The previous example, we were graphing y is equal to x squared minus 4 divided by x minus 2, where x cannot be equal to 2. As you saw previously, we factored out a common factor of x minus 2 from both numerator and the denominator. This left me with the equation y is equal to x plus 2, but x still can't be equal to 2. So what I would like to draw your attention to, this is just the equation of a linear function. So I have graphed a linear function. Well, what's the significance that x can't be equal to 2? This is called a point of discontinuity. We are still not permitted to have an x value of 2. So very simply, when you have a point of discontinuity or a non-permissible value, normally we observe a vertical asymptote, but if you don't, you must draw a circle, or I always say you must shoot a hole in your graph, basically make a hollow hole in your graph at that point of discontinuity. So let's just go and we'll switch programs and we'll start maybe asking some fundamental and answering some fundamental questions. So given an equation of a function, how can one determine asymptotes? So when do vertical asymptotes occur? Well, vertical asymptotes occur at the x values that make the denominator equal to 0. Now, if you think about it, that may make sense because a vertical asymptote just simply says f of x gets really, really large. And if we have a denominator that is approaching 0, that is, if our function has a denominator that is very close to 0, the y value will get very large. So we do have a vertical asymptote basically at our non-permissible values. There is an exception that we saw. There is an exception if a factor is canceled from the numerator and denominator, then there is a point of discontinuity. So if you're canceling out factors, no longer may you have an asymptote. If you cancel out that factor at the corresponding x value, there will be a point of discontinuity, which essentially is a hole in the graph that I showed you. So I hope that makes sense. So really, you have to look out for your non-permissible values. Really good to factor things always. Factoring really makes your vertical asymptotes stick out, and they also really draw your attention if there's a common factor for points of discontinuity. So how can we determine a horizontal asymptote? That is much more difficult, and I'm going to break it up into 3 different cases. So there's really 3 different scenarios, and they have to deal with the degree of the numerator and the degree of the denominator. So case 1. If the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote, y is equal to 0. Allow me to give you an example. So if y is equal to, I'm just going to put this in my denominator, the degree of my denominator is 2, provided that whatever polynomial expression I put up at the top, as long as the degree is less than, the degree of the numerator is less than the degree of the denominator, we will have a horizontal asymptote as y is equal to 0. So for example, I'm just going to put down another example. There we are. This also has a horizontal asymptote at 0. The degree of the numerator is 0. The degree of the denominator is 2. Let's go over case 2 now. Now case 2 kind of gets more involved, but it's not that bad. If the degree of the numerator is equal to the degree of the denominator, that is, the highest exponent in the numerator is equal to the highest degree in the denominator, Then we have a horizontal asymptote. Y is equal to A over B, where A and B are the leading coefficients of the numerator and the denominator respectively. So really, maybe some examples might clear this up. Now I'm going to perhaps give you the example. Y is equal to 3x squared over x squared minus 4. Now what we see here is that the degree is 2 in the top and the degree is 2 in the bottom. So we have case 2 scenario. So what do we have to do then? Well, what we must do is we need to look to the leading coefficients. So the leading coefficients of the numerator is 3. The leading coefficient of the denominator is a silent 1. So my horizontal asymptote then would be y is equal to 3 over 1, probably better known as y is equal to 3. Another example may be y is equal to x over x minus 2. What we notice is that the degree of the numerator in the top is 1, the degree of the denominator is 1, so we have equal degrees, so then we have to look to the leading coefficients. So now I'm just going to make two dots or two dashes, one right here and one right here, and that correspond to our horizontal asymptote. Y is equal to the coefficient of the numerator, so whatever that number is, over the leading coefficient of the denominator. So here it's 1 and 1, so it'd just be 1 over 1, or probably y is equal to 1. So if you change that to 4, then this would be 4 over 1. If you change the top to 5x, then it would be 5 over 1. Similarly, if I just put y is equal to 2x divided by 3x minus 2, well then my horizontal asymptotes would no longer be this, but would be 2 over 3. And this is under the condition that our degrees are the same. Oh, pardon me. So case 3, if the degree of the numerator is greater than the degree of the denominator, then no horizontal asymptote exists. So that's fairly straightforward, I think. Every single graph you've encountered has never had a horizontal asymptote. If I may just have a brief sketch here, I'm going to give you an example. Now, a horizontal asymptote by definition, this crazy definition, says that as x gets infinitely large, we must have a function f of x approach a constant c. So I'm just going to give you an example where there's not a horizontal asymptote, and for the function y is equal to x. We're quite familiar with that. Just a quick sketch. I'll draw my Cartesian plane here. Y is equal to x, looks something like that. And so as x gets infinitely large, the y value does not approach a constant. Instead, the y value gets higher and higher and higher. It doesn't approach a constant like 2 or 3 or 4. All right. Hopefully I haven't bored you enough here. So there is additional work here that I may attach to you to really understand your horizontal asymptotes. It's really theoretical in nature and almost takes a calculus approach. But I find that tackling this more serious, deliberate, hard work really clears up the understandings of a horizontal asymptote. But it is hard work. So let me know if you're interested, and I can put something together fairly quick. So I'm just going to say it's very critical that you factor both numerator and the denominator. And really, when you factor in numerator and denominator, it really gives up the secrets of the function, especially of our rational function. You're able to better differentiate the horizontal and vertical asymptotes, as well as points of discontinuity and whether or not factors cancel each other out. So other important points on a rational function can be determined by, well, the y-intercept is very easy. We just let x is equal to 0, and that's always true for no matter what function. Now, to determine the x-intercept, we have to determine the value where y is equal to 0. So I'm just going to look down here. And for homework, I have something to do for you to do. I want you to try to construct a common sense definition of a horizontal and a vertical asymptote. And then I want you to determine the horizontal and vertical asymptotes of questions that will be below, below these three examples. So I'm just going to do these three examples. So I would like us to calculate the vertical asymptotes. So the first thing I'm going to do with this example is I'm going to factor it. I have to practice what I preach. Right? If I say factoring is important, let factoring be important. So very quickly from this function, we can pick out our points of non-permissible values. So x cannot be equal to plus and minus 3. What a time to run out of lead and a pencil. Anyways, from this, we may be able to see my vertical asymptotes. So we have two factors in the bottom that give me my vertical asymptote, and there's no corresponding factor in the top that cancel out. So my vertical asymptote is x is equal to 3, x is equal to negative 3. My horizontal asymptote is going to be a little bit different. My horizontal asymptote is going to compare the degree of the numerator to the degree of the denominator. So what we see is the degree of the numerator is 1, the degree of the denominator is 2. So under that condition, we have a horizontal asymptote of y is equal to 0. To get my y-intercept, I simply let x is equal to 0. So if x is equal to 0, what I would get is my y-intercept is equal to 0. Now, if to get my x-intercept, I equate y is equal to 0. If I equate y is equal to 0, and I just want to draw your attention to something because this is often overlooked. So y is equal to x divided by x squared minus 9. When is this true? This is only true, so 0 is equal to x divided by some quantity. Now it doesn't matter what that quantity is in the bottom. This is only true when the numerator is equal to 0. So my x-intercept is 0. So for example here, I like making crazy examples. So if I had some weird equation like 0 is equal to a triangle divided by a square. Now when is a triangle divided by a square is equal to 0? Only when the top is equal to 0. But let's continue on. Looking at this, my vertical asymptote. Let's move on, press pause. Maybe you try to calculate your vertical asymptote, your horizontal asymptote, your x-intercept, and your y-intercept. So my vertical asymptote, you have factored this. Great work. I'm hoping you factored this. Makes things so much clearer. My vertical asymptotes come from my denominator. So I have a vertical asymptote at x is equal to 1 and x is equal to negative 1. My horizontal asymptote, what I see here is my degree of my top is 2. My degree of my denominator is 2. So we must compare leading coefficients. So my horizontal asymptote is 1. My y-intercept is when x is equal to 0. Simply when I plug in x is equal to 0 here, I have a y-intercept of 0. My x-intercept, really all I have to do is look to the denominator. My numerator. When is my numerator equal to 0? When x is equal to 0. Last but not least, maybe you want to press pause here. All right, thanks for joining me. I think I've seen this one before, right? So what we notice, what's so special about this is when you factor this out. However, it's really important to say that x cannot be equal to 2. This is fundamentally important. So we can change this into x is equal to x plus 2, but x cannot be equal to 2. What we see is that we have a vertical asymptote does not exist. There is no denominator. My horizontal asymptote does not exist. And the reason why my horizontal asymptote is, I'll go back to the original function, is because the degree of the numerator is higher than the degree of the denominator. Now my y-intercept, I can let x is equal to 0. When x is equal to 0, I can take a look at this one. I get a y-intercept of 2. My x-intercept, let's take it back to grade 9. My x-intercept, I have to let y is equal to 0, so I have to solve the equation 0 is equal to x plus 2. So therefore my x-intercept is equal to negative 2. I'm hoping this helps out quite a bit. This is a lot of abstract work right before we get to graphing. So please do the next few examples for today, and then tomorrow we'll start off with graphing a few examples and getting down to business of graphing rational equations.